All right, so let's talk a little bit about this Durbin-Watson test for autocorrelation in the residuals. Suppose that let's index the residuals. Let's re-index them by some other index set. Let's say maybe the one that indicates the order in which the observations were made, like time or something. Okay, so this stuff right here is the test statistic. Okay, it's going to always take a value between 0 and 4. Now, it turns out if this thing is substantially less than 2, then that's indicating evidence of positive serial correlation. And here's how you can kind of see how that test statistic makes some kind of sense. Let's say we plot the residuals there versus time. Okay, so this is the time index I. Okay, maybe what if you get some values that sort of go like this? Okay, so you can see that something is going on. Time is having some sort of an effect on these residuals. Is one if you have a large residual here, then the next one in time tends to also be large. Okay, so there's some sort of correlation going on there. Let's take a look at the top. That is this numerator here. Okay, if I let I be 1, then I'm looking at the difference between the second and the first residual, and I'm squaring that. Okay, so that difference is this much, right? These are the residuals, and so if I square it, I get the area of that square. Okay, and then if I look to the difference between the next two, I get the area of that square, and then the area of that square, and the area of that square, and so forth and so on. And I add up all the areas of these little squares here. Okay, so that one's like that, and then anyway, you're going to get a bunch of little squares here that you add up, and okay. Okay, something like that. Now, what does the bottom look like? Well, let's do this in red. What does this stuff look like? If I sum up these squared residuals, I'm actually looking at, here I'm actually summing up. Now, for some reason, I can't write over here. I'm finding the areas. Finding these areas, right? Looking at the data points, dropping down to 0, right? Finding the actual squared residuals, okay? Okay, and so that sum of squares is going to be larger, at least in this case. Whoops, got a little carried away there. Anyway, you can kind of see what's going on here. We're comparing those two sums of squares, and in this case, where you see some of that autocorrelation, you're going to see that sum of squares in the bottom is larger than the sum of squares in the top. Okay. Now, let's just for fun here, let's compare the expected value of the numerator to the expected value of the denominator here. So that is under, so given H naught, which is that these error terms are independent normals with mean equal to 0 and variance equal to sigma squared. Okay, given that they're independent normal with mean 0 and variance sigma squared, then what is the expected value of the numerator? Expected value of the numerator there. It's the expected value of the sum. I goes from 1 to n of these e sub I plus 1 minus e sub I quantity squared. Okay. Well, first of all, I know that these differences are good. Whoops, I got this thing on the wrong side of the tracks there, because right there. This is just going to be equal to n times the expected value of 1 squared difference. All right? Okay. Squared. Okay. And if in fact these things are independent, then I can replace these. They don't have to have had occurred next to each other in time. I could just say it's the expected value of the square difference of, we'll say E1 and E2. Okay. Any of them. Okay. Or EI and EJ, however you want to say that. Now this is n times. I'm just going to FOIL this stuff out in here, plus E2 squared minus 2E1 E2. Remember, these errors are in fact random variables. Okay, so let's see, what can we do here? I'll bring this expectation inside here. This is going to be n times the expected value of E1 squared plus the expected value of E2 squared minus 2 times the expected value of E1 times the expected value of E2. Okay. By the way, I can do this step, right? All I've done is I know that the expected value of the sum is the sum of the expectations, right? So I'm just bringing this expected value in on each one of these terms. On this last one, though, I know that by the independence assumption on these error terms, then if two random variables are independent, then the expectation of their product is the product of their expectations. You learn that in the probability class. Okay, so then I'm left with n times, hey, you know what? These expectations should be the same, right? Because E1 and E2 behave the same. So I could just say that this is 2 times the expected value of E1 squared, right there. And then minus, hey, you know what? These means are the same. They're both mu's. Minus 2 mu squared, right? I'll factor out the 2, and I get 2n times expected value of E1 squared minus mu squared. Hey, you know what? This is just the variance of an error term. So this is 2n sigma squared. That's what the numerator evaluates to. What does the denominator evaluate to under the null hypothesis? I'll do that over here. If H naught is true, then that is, if I take the expected value anyway, expected value of the sum of these squared errors is, well, this is, again, all these behave the same, so this is just n times the expected value of any one of those, the expected value of any one of those squared, and then that's equal to, hey, look, can I write it like this? E1 minus 0 quantity squared, right? No problem with that. But hey, look, 0 is, in fact, the expected value of any one of those error terms, right? So, in fact, this is just the variance of an error right there, the expected squared difference between the random variable and its mean. So this is the expected value of the denominator. Hey, what happens if you take 2n sigma squared? If I divide the expectations, 2n sigma squared over n sigma squared, you get 2. Okay. So the idea here, and this is sort of not exactly hardcore theory here, but the idea is that if the null hypothesis is true, you'd expect this test statistic to be, probably somewhere around 2. If it's really small, like you see here, then you get these. That's indicating some sort of serial correlation here, and the black, the total area from the black squares there corresponds to the numerator. The total area and the summed up in the red squares corresponds to the denominator, and the total area in the black then over the total area in red would be substantially less than 2. The von Neumann-Durbin-Watson test can be carried out in R, as we'll see in this next video.